to develop a quantitative model of the Moeller-Gibbs energy, we want to think about how the Moeller-Gibbs energy is affected by temperature and pressure. Let's first focus on the temperature dependence. And so to visualize at least what's going on, let's think of a pressure versus temperature diagram. And let's look at the region in which we transition from an alpha phase to a beta phase. Okay? If you want to make this a bit more concrete, you could think of alpha being the solid phase and beta being a liquid phase. Okay? And what we're going to do is we want to look at how the phases change from alpha to beta as we stay at a constant pressure. So let's say we're at pressure P naught, and then we just vary temperature. Okay? So this is our temperature axis. And this line right here that demarcates the transition, or demarcates the alpha and the beta phase windows, this is what we're going to call T alpha to beta. And so if you're thinking of the solid to liquid transition, this would be your melting point, your melting temperature. Okay? All right, and so this is, what we're trying to describe mathematically. This is what it would look like on a pressure versus temperature diagram. But what we're ultimately interested in is how the Moeller-Gibbs energy changes as a function of temperature. Okay? And so if we plotted Moeller-Gibbs energy versus temperature, we could look at, and we could want to ideally calculate what the Moeller-Gibbs energy is of each of the phases. Okay? And so let's say, for example, that this line represents the Moeller-Gibbs energy of the alpha phase. Okay? And then this line represents the Moeller-Gibbs energy of the beta phase. Right? And so we see that at low temperatures, the Moeller-Gibbs energy of the alpha phase is less than the Moeller-Gibbs energy of the beta phase. And so in this region, since alpha has the lower free energy, the system or the chemical would want to be completely in that alpha phase. At higher temperatures, though, we see that the Moeller-Gibbs energy becomes lower than, for the beta phase, it becomes the lower one, right? And so at these higher temperatures, that's when the chemical substance, it completely stays in the beta phase. And it's at this point right here when alpha and beta have the same Moeller-Gibbs energy. That's what we call the T alpha to beta temperature. Okay? And so just to hammer this in, as you go to temperatures above that T alpha to beta, the system transitions to the beta phase because the Moeller-Gibbs energy of G beta, or the beta phase, becomes less than the Moeller-Gibbs energy of the alpha phase. Okay? Right? So conceptually, that's what's going on. That's why we see the material go from the alpha to the beta phase as you increase temperature. Okay? One thing I want to point out is that for these Moeller-Gibbs energy functions, the slope this G molar or molar G dt at constant pressure, we know from the fundamental Gibbs equation that that's equal to the negative of the entropy. Okay? All right, and so this is at least, what's going on when we see the chemical go from the alpha to the beta phase. But to gain a little bit more insight about what's going on, what we could do is we could split up that molar Gibbs energy function into its enthalpic and entropic parts. Okay, so we know that the molar Gibbs energy is equal to enthalpy minus T entropy. Right, that's just the definition of the Gibbs energy. All right, and so what we want to do is we want to think about how the enthalpy and the entropy change as a function of temperature. Okay? All right, and so when we think about this, what I want to do is when we think of the beta phase, we're going to assign the beta phase as a phase that has higher entropy. Okay? And this is just by convention. And so, for example, if we were looking at the transition from a solid to a liquid, liquids have higher entropy than solids, so the beta phase would be the liquid. Similarly, if we were looking at the transition from a liquid to a vapor, in that case, the beta phase would be the vapor phase. Okay? All right, in any case, and so we want to look at how enthalpy and entropy, how do those things change as a function of temperature? Okay. And so what we could do is we could think about plots of enthalpy versus temperature. And if we had an experiment where we measured the enthalpy of a substance as a function of temperature, what we would see is something that looks like this. Okay? All right? And so there's kind of three important regions on this plot. 1, 2, and then this jump here would be region 3. Okay? All right, and so in region 1, what we're looking at here is how H changes as T changes, right? And so essentially, we're looking at dH over dt, and we know by definition that that is the constant pressure heat capacity, right? Right. So at low temperatures with enthalpy, what we would be looking at is the constant pressure heat capacity of the alpha phase. Similarly, at the high temperatures, that slope there corresponds to Cp of the beta phase. Generally, if you look at two different phases, the heat capacity of the alpha phase is generally not equal to the heat capacity of the beta phase. And the reason for that has to do with just how the molecules behave when they're in the different phases. Okay? In any case, this third region right here, so we see as when we heat the substance up to a certain temperature, which is that T alpha to beta temperature, we see that the enthalpy jumps up, becomes discontinuous, and then continues on into the beta region. And so that jump that we see with enthalpy, that corresponds to the latent heat of the phase transition, or the transformation. So this is something that we talked about in MEB2. And so you have different types of latent heats. And so you have the latent heat of vaporization, or enthalpy of vaporization. And so that would be when you go from the liquid to the vapor phase. You have your enthalpy of melting. That's where you go from the solid to the liquid phase. And you also have the enthalpy of sublimation. And that's where you go from the solid phase to the vapor phase. Okay? All right, and so the reason I bring these up now is because these latent heats, these enthalpies, these are all things that could be measured in an experiment. Okay? And so if we're trying to model how the Gibbs energy changes, it's important to know these parameters. Okay? All right, and so that was sort of the behavior of enthalpy as a function of temperature. We could develop a similar plot for entropy. Okay? Where region 1 is here, region 2 is up here, and region 3 is here. Okay? All right, and so in region 1, the slope there corresponds to the heat capacity divided by temperature, right? And so that comes from the fundamental entropy equation. In region 2, that's also Cp beta divided by temperature. And then region 3, that's what we call the change in entropy as we go from the alpha to the beta phase. Okay? All right, and so I bring all these things up because tying this back to the molar Gibbs energy, when we reach that transition temperature, T alpha to beta, we know that at that temperature we have both the alpha and the beta phases are in equilibrium with each other and they could coexist. And so the criterion for that is that G alpha, or not G alpha, G beta minus G alpha, that difference is equal to 0. We also know that delta G is described by H minus T alpha to beta delta S alpha to beta. Right? That's just, those are the things that make up delta G. Since delta G is equal to 0, what we could do is we could rearrange this equation so that we get delta S, the change in entropy as we go from the alpha phase to the beta phase, that's going to be equal to the change in enthalpy divided by the transition temperature. Okay? And so what that means is that because both of these things can be directly measured, what that means is we could determine the change in entropy from those measurable properties.